In a time where AI work is getting reduced to sending HTTP requests to an LLM, we are going to go back to the basics, back to when training AI models was done on your CPU, and when you had to use a neural network, you had to implement your own backpropagation. So the goal of the series is to implement a PyTorch-inspired deep learning framework from scratch in C++ to gain more insights into how deep learning actually works, and eventually also use this framework to train our own MNIST classifier. In our last video, we implemented modules, as we don't want to define our neural networks using our tensor class directly, but instead want to use higher level building blocks which manipulate tensors and also allow us to easily define common operations in the neural network. This is also how PyTorch does it. We implemented a flatten module, and for every module we have to implement a forward method which takes a input tensor and produces an output tensor. For the flatten module, the operations just takes in a tensor of any shape and reduces it to a single dimensional tensor. We also implemented a linear module which, given an input tensor, multiplies it with a 2D tensor and then adds a bias to it, which is a one-dimensional tensor. We also implemented a ReLU module, which just turns all the negative numbers in a given tensor to 0, and this allows us to introduce some non-linearities in our neural network, which makes it capable of learning more complex relationships. If you don't know what any of this means, I would just recommend you to watch the last video, as I clearly explained everything over there. So what this allowed us to do was, on the left we have our original PyTorch MNIST classifier, and after the last video we could re-implement this one with our own neural network. As you can see at the top, we define the layers, then we also implement a forward method which just passes the input through all the layers and returns it. So let's get started with the episode, and you can see how excited I am about this episode, as I even included some thunderbolts, because today we are doing something very exciting, and that is figuring out how we can make this network actually learn something. Because when you just define a neural network, you initialize it with some random numbers. So initially it will just be like a slot machine outputting some random numbers. And what we actually want to do is make the network, of course, learn some task. And I will, for example, demonstrate this by looking at Breaking Bad. Not that Breaking Bad is anything special, I just like the series. But we need some way, for example, in the series, Walter is trying to learn Jesse how to produce some very illegal product, and the way you, of course, need to you need to have a way on evaluating someone, and the same is with a neural network. And in Breaking Bad, this is done by measuring the purity of the product that they produce. For example, in the beginning of the series, the product Jesse produces is 43% pure, and the product Walter produces is 99% pure. And with our neural networks, we also need to have some kind of measure of how good our neural network is doing. And that is what is called the loss function. And loss is just a measure of how close the produced output of our neural network is to the intended outputs. And also the interesting thing is, you of course know AI is getting used a lot for a lot of different use cases, from self-driving cars to predicting, classifying images, to actually generating text. So you might think there are thousands of loss functions, as there are a lot of different tasks for which we use AI. But the cool thing is that there are only a handful of loss functions that are actually used in practice. And the same loss function can be used to learn a wide variety of different tasks. So let's take a look at one of those loss functions. For example, let's take this example of where we want to use a neural network to to predict the temperature based on the time of day, the actual date, and the humidity. Given these inputs, which we of course will turn into a tensor, the network will output a number, let's say 7, which we will interpret as the predicted amount of degrees. But although the network predicts 7 degrees, we see, for example, in our dataset that for the exact same parameters, the actually measured value is 12 degrees. So the loss function in this case for such a regression task, this is called because we are predicting a real number, not some preset amount of classes. And for a regression task, what is often used is the mean squared error. And what this will measure is we are basically going to subtract each value in the tensor of the true label with the corresponding number on the output tensor of the prediction. And in our case, this will just be single numbers. And afterwards, we of course divide by the amount of numbers in both tensors. But for our case, in the example, this is very simple, as the real label is 12 degrees, while we are predicting 7 degrees. So let's just subtract both values, square it, and you can see that that we get a positive number. And the lower this number is, the better that our network is at predicting, because we get the lowest value if actually the two tensors have the same number on each position. But our task is a bit different. First off, this is not a regression task, but a classification task. As given an MNIST image input, what our network will do is output a tensor of size 10, where each number will be associated with a prediction for the output. So this is basically the confidence that the network thinks that the number is 0. This is the confidence that the number is 1. And the last value will be the confidence that the number is 9. And larger numbers just mean that the network has more confidence. So it probably here thinks that the number 8 has the most amount of confidence. So you can just map each index to the confidence that the neural network has that this is the right class of the input. And also a thing you need to know, in our test set, each image will be represented by a single number, by a single true number. And this true number, also called true label, we will have to one-hot encode that. And what this means is you just take a vector, a tensor of the same size as the amount of classes that there are. So a size of 10 numbers. And you basically turn everything to 0 except for the index in the tensor that is associated with the true label, which is in this case 5, as the first number is associated with 0, 1, 2, 3, 4, 5. So this just indicates that for this input, the true label is the number 5. So now we have both the true label in a tensor and the prediction in a tensor. So do we just apply the mean squared error that we just saw? What do you think? Let's find the answer somewhere down below. Well, no, because we are actually going to use the cross entropy loss. There's probably a mathematical reason for this, but I think people just found also out in practice that the mean squared error doesn't work that well with a multi-class classification task, because what we are doing right here is a multi-class classification task. As for each input, only a single class is true. So it's clearly not a regression task, and multi-class classification task, as I said. And for a multi-class classification task, you use the cross-entropy loss. And the way this cross-entropy loss works is you first off turn your raw model outputs, which are also called logits, you turn them into probabilities by applying the softmax function. And the softmax function, basically at the number at every position, it takes the exponential of that, and then it divides it by the sum of the exponential of all the other numbers, including the number itself in the tensor. So this will produce a tensor of outputs where each number is between 0 and 1, and this will represent the probability that the neural network has and that this specific number, for example, is the true label. And of course, we still need to have the true labels as well to calculate the loss. And just applying the softmax isn't enough, but now we can actually calculate some kind of loss, and that will be the negative log likelihood loss. And the negative log likelihood loss, what it does, it will just iterate over all the values in both the true label tensor and the softmaxed tensor, and it will multiply the number at position I in the true tensor times the logarithm of the softmaxed output at position I, and it will take the negative of that. And what cross-entropy loss then basically means is just first apply a softmax on the raw model outputs and then do the negative log likelihood loss. And we can simplify this a bit because we have a multi-class classification task, only one E will be actually 1 because there's only one true label for every sample. So this can basically be simplified just to this, the negative log of the softmax of the prediction that corresponds to the index of the true class. And because every number after being softmaxed is between 0 and 1, we can plot it as follows. And so basically, if we assign a probability of 1 to the true output, the loss will be 0. And if we assign a very low probability, well, then the loss will simply increase. So this also corresponds intuitively to what we would expect. Okay, so a neural network can basically be represented, I've already repeated this, but it can be represented as a series of tensor operations once you go a level lower than the actual modules. And in every tensor, we have implemented this in our tensor class C++, we are building a computation graph by, for every tensor, for example T3, keeping track of the parents. We also have a gradfn function, which is capable of updating the actual gradient of the parents. And we also have a backwards method in a tensor, which is meant to be called on the eventual output and will just iterate through the entire graph in backwards order and called the gradfn method to then finally arrive at a gradient for each tensor. If you need a better understanding of this, I strongly suggest watching the third part of this series, as I went through a lot of derivations of the gradfn of the plus and the multiplication. So yeah, I don't think my explanation will be as clear unless you also watch that part. But we now have two new operations. First off, the softmax function, and then also the negative log likelihood. So let's go on and derive this gradfn function for our softmax. And the gradfn function, as you know, we need to calculate the derivative of the loss with respect to some weight. and this will just be equal, if you apply the chain rule, to the derivative of the loss with respect to the function in which the weight was used, times the derivative of that function output with respect, taking the derivative of this function output with respect to the weight itself. And in this case, the function, let's first start with the softmax. And what the softmax does is, we've already seen this formula now, so it takes a series of weights, these are numbers, and we applied this operation to turn them into probabilities. And in my third video, I derived all of these myself, this multiplication and this addition, because the eventual derivative formulas were very simple to implement. But as you can see, this is a bit harder. There is a division here, and the same weight is used multiple times in all these tensor outputs. So I first started deriving it manually, but eventually I derived a very, very ugly formula, which is very hard to implement in C++. So, and as I'm no mathematical god, the thing I did was I just went searching online, and I found this very, very good article of Thomas Kerbiel, which derived the softmax function for us. And if you already look at them, you know this is going to be a good machine learning article. Maybe if you watch like all my videos after one another, I think it will set you on your way to becoming someone like Thomas, but even I have not reached this level of competence. So let's just look at the proof that he is doing. So instead of calling his initial tensor W, he calls it C, and he then also applies the softmax function on Z, which will yield an output tensor similar as above. He will then associate he will basically call each of these numbers here Si. So this is S1, this is S2, this is S3, Sn I mean. Just to refer them, just to be able to refer them within the formula. And what you should do to derive the derivative of the loss with respect to a specific set J then is basically take the sum of all the i's of the outputs of the softmax. So because we also need to propagate potentially the gradient of the output, and then we need to, for each Si, for each set J I mean, we need to know how much we need to sum the derivative of the loss with respect to the softmax I, and then multiply it with how much this Si, the derivative of that to set J. And what I would do, okay, this part is already given by when we call the backward on our computation graph, we already know the derivative of the loss with respect to the output of the softmax, and we only need to derive this part, and I would start deriving, just basically calculating this with respect, calculating the derivative of this with respect to Zj. But what Thomas says is no, just wait for a while. What we are going to do, he says no in a very super chat Dragon Ball Z form, and what he says is no, we are first going to take the logarithm of Si and write that formula derived to Zj. And the derivative of the logarithm is just 1 over the thing inside the logarithm, which in this case is the softmax of I, and then the chain rule tells us that we then also need to calculate the derivative of Si with respect to Zj. So what he then does is rewrite this formula a bit to this part, and to do that you just need to multiply this part with Si, as you can see right here. So he just rewrites the formula a little bit, and what he then goes on to do is basically check what actually is the logarithm of the softmax of I. And the logarithm of the softmax of I is basically the logarithm of this function, the softmax of I. And as you probably know, the logarithm of a division is just the logarithm, no, not the log, yeah, it's the logarithm of the upper part minus the logarithm of the denominator, and the logarithm of the exponential is just the exponent, so it's just zi minus then the logarithm of the denominator, so he writes it out like this. And what he then does is, but wait, what is then the derivative of this with respect to zj? So let's calculate the derivative of this with respect to zj. So the first part is just zi, derivative of zi with respect to zj, minus the derivative of this logarithm of exponential summed with respect to zj. And let's calculate this a bit further. And the first part can basically be simplified as follows, because we know if we take the derivative of zi, which is just a single parameter, to zj, which is another parameter, the derivative will be 0 as the output zi, a decrease in zj or a decrease doesn't actually do anything to zi, so the derivative will be 0 unless actually the index j is I. In that case, we are calculating the derivative of zi to zi. So it will basically be 1 if I is j, and in the other case, this part will be 0. And the other part, once again, the derivative of a logarithm is 1 over the thing inside that logarithm. And then we apply the chain rule once again. So we take the derivative of this inside part with respect to zj. And this is a huge sum. So it's actually z1 plus e to the z2 plus and so on until we reach e to the z n. And if we take the derivative of that with respect to zj, we only need to take a look at the part that actually contains zj, which will only be e to the zj. And if we take the derivative of that with respect to zj, it will just be e to the zj, as that is a rule of derivatives. So this part will also be simplified to e to the zj. And what you should then recognize is that this is actually once again the formula of the softmax with respect to j. So we once again rewrites or refers to this part as the softmax of j. So and what we can then do, we've finally derived this logarithm of si with respect to zj. So we can plug it in this part above. So we just need to multiply the thing we have just derived with si. So that's what we do right here, si times what we derived here. And we finally have a formula for the derivative of si with respect to zj, which was what we were searching all along. And this can be written very simply as if the derivative of si with respect to zj, if I is equal to j, this becomes 1. So this is the formula. And if I is not equal to j, this becomes 0. And this becomes the formula, which is much simpler than anything I could have derived myself. And I'm very thankful to Thomas for deriving this for me, as we now have a very easy method of implementing our credFn as, we just need to use this formula, and this part of Si with respect to Zj, we can just use this formula for that, which just depends on some softmaxes. As the softmax is a building block used in our neural networks, we are once again going to inherit from the public module class. This will require us to override the forward method, which will take as input a tensor and output a tensor with the softmax operation applied. If you don't know what modules are and why we need them, I would strongly recommend you to watch the previous part of the series, as I implemented many modules from scratch and explained why they are very helpful for building neural networks. We are only going to define the softmax operator for scalars and 1D tensors. This is the same as in PyTorch. For a scalar tensor, the softmax method is trivial, as the result will be 1. If we are required to track gradients, we will also implement the credFn function, which updates the gradients of the parents in the backward pass. In this case, the gradient to the parent tensor will be 0, as the result is constant. This is also the reason why softmax shouldn't be used for binary classification, but you should instead use the sigmoid function. We then make a shared pointer to the result while building the computation graph by keeping track of the parents and the gradient of the operation. If you're unfamiliar with this credFn syntax or what is happening here, I would recommend you to watch the third part of the series, as it's explained there. The 1D case is more interesting, but don't stress, as we've already derived everything we need to know to implement this one. We are first going to search for the maximum value in the input tensor. As you can see, we will use this to normalize the input tensor by subtracting each value from this maximum before calculating the softmax function. We do this to try to prevent potential overflow, as the exponential can become a very large number. We store the softmax in a vector which is named S, so that the eventual formula will really closely represent what we have derived before. Now, if we are required to calculate gradients, we are going to implement the logic we derived. We need two indices for this, an index j, which represents the index of the element of the input tensor towards which we are calculating the gradient. Then we are going to use the index I to loop over all the output gradients, and depending on if I is equal to j, we update the gradient to j with the corresponding formula we just derived. We then push the gradient to j to our gradient vector. We make it such that in the backward pass, when this function is called, the gradient to the parent tensor, which is called input, is updated, and finally return shared pointers to the output of the softmax operation. Okay, we still have to do one more mathematical derivation, and that is calculating the derivative for the negative log likelihood. If you hate mathematics, just like I did in high school, I promise you this will be the last derivation of this series and will also be relatively easy. So what the negative log likelihood does is, you've seen the formula before. It takes as input a tensor of softmaxes and also a one-hot encoded tensor of the output. And because the output is one-hot encoded, this part of the true labels is one-hot encoded, the formula basically simplifies to the just taking the negative of the logarithm of the softmax of the number on the position, which corresponds to with the same index that has a 1 on the intended output tensor. And if we then take the chain rule and calculate the derivative of the loss with respect to a specific number on the softmax tensor, it comes down to this. And first, let's take the case where I is not equal to the true class. And in that case, the function, the negative log likelihood, just becomes 0. Because as you can see, it only depends on the softmax of the true class, it just becomes 0. And of course, the derivative of 0 with respect to a certain parameter will always be 0, as the output is 0 always, so it doesn't matter how much we move Si, the derivative of this will be 0. And also for the other case where I equals the true class, we just have then to first off propagate the derivative of the loss with respect to the negative log likelihood, and then multiply it with the derivative of this with respect to as dc. And this is a very simple derivative, as it will just be equal to -1 divided by the thing inside the logarithm, and that is this. So let's also quickly implement that. For the implementation of the loss, I am once again going to stick close to how PyTorch implements this. So let's first define a loss module from which all our loss functions will inherit. Every subclass of module should implement the forward function, which takes as input an input tensor and produces an output. But a loss function actually requires both an input and target tensor as input. So let's override the first function and return an error that the loss function requires both an input and target tensor, and then implement a new virtual method and operator which takes both an input and target tensor. In C++, a virtual method can be overridden by a subclass. For the module itself, the implementation of the forward method will throw an error, as this method is meant to be overridden by subclasses, and the operator method will just call the forward method, similar to how we do it with module. Let's now define a negative log likelihood loss function, which implements the logic we derived. We make sure that both the input and target are of the same size. We then calculate the loss by finding the index of the true target class and then taking the negative of the log of the probability the network assigns to the target value. We clamp this probability to a small number, as we don't want to take the logarithm of 0. If we are required to track gradients, we will once again be keeping track of the parent tensor and define the grad(n) function. The gradient to each of the parent tensors will be equal to the output gradients times the inverse of the negative of the input, or will be 0, depending on if we are calculating the gradient to the true target class or not. We then once again return a tensor as the result. Now we can finally define our cross-entropy loss function. As I explained, cross-entropy loss first applies a softmax function on the input and then takes the negative log likelihood loss. As we have already implemented both of these operations, our implementation is very straightforward. So now we know how bad our network is doing with the loss function, but we still need to move the actual weights in a way such that the loss function decreases and that our network is actually learning. And that is what's being done with an optimizer. And I've already shown you this before, but now we know after moving all the way from our inputs to eventually to outputting a loss, we basically know how bad our network is doing at predicting. And after we have this value, we can call the loss the backward method on the loss, which will calculate the gradients of each of these tensors with respect to the loss. But now we still need to have a strategy on how to actually update the actual weights of each tensor by using the gradient. And for some intuition, we start, for example, with a certain randomly initialized value for a certain weight, and we can calculate at each time the derivative of the loss with respect to that weight. And in this case, the gradient will be smaller than 0, because if we increase W0 with a bit, we can see that the loss decreases, and because we actually want to decrease the loss function, we should actually increase W with a bit. So this means that if the gradient is negative, we want to move in the positive direction. But for example, if we were on this part of the graph, the gradient would actually be positive because the loss function goes up if we increase the w with a bit. Then we actually want to decrease our weight. So once again, we are moving in the opposite direction of the gradient. But still, there are a lot of strategies. Even if we know the gradient and which direction we should move the weight in, we don't know. There are a lot of strategies for determining how far we are going to move the weight. And you don't want to increase or decrease the weight by too little, as else it will take a lot of iterations until we eventually reach the lowest loss possible. But also, if we move too far, we might, for example, end up all the way right here and then decrease the weight by way too much and once again end up right here and never even reach the lowest value of the loss. So there are a lot of strategies for determining how much the loss should actually be increased and decreased. And that is what PyTorch implements in this Torch Optim package. And the one I probably use the most, optimizer I use the most, is called Atom, which does something very smart with using momentum. And if, for example, we are updating the gradient a lot of times, if the gradient multiple times consecutively is, for example, positive, we are then going to increase the W by way much more than when the gradient is shifting between negative and positive. But for now, for this video and for my framework, we are just going to implement stochastic gradient descent, which is the easiest optimizer. And what stochastic gradient descent does is it takes your current value of a specific weight and it subtracts the derivative of the loss with respect to that weight times the learning rate, which will be a very small number, for example 0.01. So we multiply the learning rate with the gradient and subtract that from the weight, and then we get a new weight and we repeat this process, and that is how we optimize. So this is very simple. And our training loop, so if you want to know how all of this fits together, will also then be very simple. We first off define a neural network. We define an optimizer, which has access to all the parameters of our neural network, so all the tensors we actually want to move the weights of. And then we are going to iterate for a certain number of epochs, and the epoch means how much times are we going to go over our entire training data set. But for each epoch, we divide the training data into batches, and each batch, for example, contains 10 input images. And then this is called batch. And then we are going to pass this batch through our neural network and calculate, and then we get a loss for that specific batch. How bad our network actually was at predicting the specific batch. And after we have calculated this loss function, we can call loss.backward, which will iterate through the entire computation graph in backwards order, call this grad_fn function on each parameter to calculate the gradients of the loss with respect to each parameter. Then we can call the step method on our optimizer, which will use these gradients to update the actual data. And finally, we will call zeroGrad to once again reset all these gradients to 0. So in our next batch, we can once again calculate only the loss for that batch and not have the previous gradients affect the gradients to the new batch. So let's implement that. We define a stochastic gradient descent class, which should be able to keep track of the parameters of the neural network it needs to optimize. Parameters are just pairs of string labels together with the tensor containing the weights. We also should keep track of a learning rate, which determines how much we are updating the weights at each step. The constructor takes as input both these params and a learning rate, which by default is set to 0.001. The implementation is simply just assigning these parameters to our private members. We can also define both a step and zero-grad method. The step method loops through all the parameters, and because each tensor keeps track of the gradient, which we assume is calculated before the step method is invoked, we can just update each value of the data of the tensor with the negative of the learning rate times the corresponding gradient. The zero-grad method is also straightforward and just sets the gradient of each tensor to 0 so that we can start accumulating new gradients for the next batch. Congratulations, you reached the end of the 5th part of the series, and if you understood everything, you now have a good intuitive understanding of what loss functions are, what gradient descent is, and how these neural networks are actually optimized under the hood. We have also now implemented everything we need to recreate and train our PyTorch MNIST network in our own C++ framework. So the very next video will also be really interesting, as we will train our neural network and compare it against how well the network was performing in PyTorch. So that is going to be a very exciting video, and if you want to watch it, make sure to subscribe. I hope you enjoyed this video, and I hope I see you in the next one.